In this video we define the Gibbs energy and we can see how it can be used to predict the spontaneity of any process. Alright, until now our criterion for spontaneity has been based solely on the second law of thermodynamics. Right? And the gist of the second law is that for any spontaneous process, the change in entropy of the universe must increase. Okay, that's what happens for a spontaneous process. Now, you can apply this law to any process regardless of what the conditions are. Constant volume, constant pressure, constant temperature, or not. Okay, it always works. Now, the idea then is that to calculate that value of the change in entropy in the universe, you need to consider both the system and the surroundings. Right? So we have that delta S of the universe is going to be equal to the delta S of the system, and then the delta S of the surroundings. Well, great. Now, in the calculation of the change in entropy in the surroundings, we actually saw that these deltas of the surroundings were simply the heat transfer to the surroundings over the temperature, okay, which is the same thing as the minus Q system over the temperature. And here, the idea is that if you're working at constant pressure, and that is important, okay, this the heat is going to be equal to the change in enthalpy in the system. So then you're going to end up with something that looks like this. All right? So we come to this equation and say, well, delta S of the universe is equal to delta S of the system minus delta H of the system over T. And this has to be larger or equal than 0. Okay, for a spontaneous process. Again, notice that this only works if you're working at constant pressure. Okay, but something nice happens, and that is that the calculation of the change in the entropy of the universe only depends on properties of the system, which is something that is very attractive to us because we know how to handle the system. Right. So again, look at this. If you're working under conditions of constant pressure, and also of constant temperature, that's what this T here is actually forcing you to do, at constant pressure and constant temperature, then your prediction of spontaneity only depends on the system. Okay? We can take this a step a little bit further and simply do the following. We can divide this delta S of the universe by over T, and then you're going to come to an expression that looks like this. Delta S of the system minus divided over A divided over T. Actually, let's think about this a little bit. We're going to multiply through by delta S, right? So by T. So T delta S of the universe is going to be equal to delta S of the system minus delta H of the system. This looks a lot better. And because temperature is always positive, then you're not changing the sign. Still, if this is larger or equal than 0, and you're working at constant pressure and constant temperature, then process will be spontaneous. Okay, great. So from here is where we now introduce a new thermodynamic variable that is called the Gibbs energy. Right? And the Gibbs energy is simply defined as follows. The Gibbs energy is going to be equal to the enthalpy minus the product of the temperature and the entropy. All right, and we're going to see how that definition of the Gibbs energy allows you to predict the spontaneity of a process if you're working under constant pressure and temperature. Okay, so let's go for it. Generally in thermodynamics, we're not interested in the absolute value of the Gibbs energy or the enthalpy or the internal energy. We're always interested in changes. Okay, so let's calculate what the change in the Gibbs energy would be if we're working at constant pressure and constant temperature. Okay, so we're working at constant temperature. The idea here is that this is going to be equal to that. Okay, when you're working at constant temperature. And again, if this is now the system, we can say that everything depends on the system. All right, so now we're going to compare these two expressions. Look what you have right here. And look what you have right here. They're exactly the same thing, but with opposite sign. Okay? What that means is that if you're working at constant pressure and constant temperature, then this delta G system being negative is also a criterion for spontaneity. Okay? So notice what we've done right here. We know that the second law predicts the spontaneity of a process for any set of conditions. However, if we're working under constant temperature and constant pressure, and those are conditions that we really like to use in chemistry, especially for running chemical reactions or a variety of processes, right? Under those conditions, it turns out that the calculation of the spontaneity can be a little bit simpler because you don't have to think about the whole universe. You can get that prediction of spontaneity just based on a property of the system, which is the Gibbs energy. Okay? The case of the change in entropy of the universe, that has to be positive. In the case of the change of Gibbs energy of the system, that has to be negative. And again, this only works if you're working at constant temperature and pressure. Needless to say, every time that we're working at constant pressure and temperature, then we're going to be using the Gibbs energy to predict spontaneity rather than trying to calculate the change in entropy of the universe. It's more direct, it's simpler, and again, it avoids the calculation of the entire system and surroundings partition that we have to use in the calculation of the change in entropy of the universe. All right, so in this video we have seen how you can define a new thermodynamic variable that is called the Gibbs energy that allows you to predict the spontaneity of a process just by looking at properties of the system. Okay? And what we're saying is that the definition of the change in Gibbs energy at constant temperature and pressure is equivalent to that of the change in entropy of the universe. The only difference is that for a process to be spontaneous, the change in Gibbs energy has to be negative, but then the change in entropy of the universe has to be positive.